When an axial force acts on a bar, the bar changes length. That simple statement becomes much more interesting when the force, the area, or even the shape changes along the bar. In this lesson, we will build the complete idea slowly. We will begin with a uniform prismatic bar, develop the general integral equation, apply it to stepped and tapered bars, study deformation caused by the bar's own weight, and finally solve a fixed stepped bar problem using equilibrium and compatibility. Keep one physical idea in mind throughout. Each very small slice contributes a very small change in length, and the total deformation is the sum of all those contributions. Consider a straight uniform bar of length L, cross-sectional area A, and Young's modulus EA concentric tensile force P acts along its axis. The average normal stress is P divided by A. Under linear elastic behavior, strain is stress divided by E. Therefore, the axial strain is P divided by AE. Strain is also change in length divided by original length. Multiplying the strain by L gives the familiar expression delta equals PL divided by AE. Notice the assumptions behind this compact equation. The bar is straight and slender. The load is axial and concentric. The material remains linearly elastic, and PA and E remain constant over the length being considered. Now allow the internal axial force, the area or the material stiffness to vary with position x. Take a differential slice of thickness dx over this tiny slice. The quantities are locally constant. Its small deformation is d. Delta equals n of x multiplied by dx divided by a of x times e of x. Here n of x can be positive or negative. Positive n means tension and produces elongation. Negative n means compression and produces shortening. Integrating from 0 to L adds every slice contribution. The general equation is delta equals the integral from 0 to L of n of x over a of x e of x dx. Every special case follows by choosing the correct functions and limits. A stepped bar is divided into segments within which the axial force, area, and modulus are constant. We do not need a new theory. We simply apply PL over AE to each segment and add the signed results. Thus, total deformation equals the summation of n sub I, L sub I divided by A sub I, E sub I. Before substituting values, cut each segment and determine its internal axial force from equilibrium. Then assign its sign. A tensile segment contributes positive deformation. A compressive segment contributes negative deformation. This sign convention is essential. A long segment with a small area may dominate the total response, but a compressed segment can cancel part of the elongation from another segment. The final result is an algebraic sum, not a sum of magnitudes. There are two useful intermediate cases. First, suppose the internal force is constant, but the area changes with x. Then delta equals the integral of P divided by A of xe dx. Second, suppose the area is constant but the internal force changes with x. Then delta equals the integral of n of x divided by AE dx. A bar carrying its own weight is an example of varying internal force because a section near the top supports more material than a section near the bottom. When both force and area vary, use the complete expression. The procedure is always the same. Choose a coordinate, write n of x, write a of x, check units and signs, and only then integrate over the stated limits. Consider a flat bar with constant thickness T. Its width changes linearly from B2 at the loaded end to B1 at the fixed end. Measure x from the end having width B2. Linear interpolation gives B of x equals B2 plus the quantity B1 minus B2 multiplied by x over L. The local area is T times B of x. Because the axial force P is constant, the differential deformation is P dx divided by ET B of x. Integrating from 0 to L produces the logarithm. The result is delta equals PL divided by ET times B1 minus B2 multiplied by the natural logarithm of B1 over B2. As a useful check, if B1 approaches B2, the limiting value becomes PL divided by ETB, exactly the uniform bar result. Now consider a circular bar whose diameter changes linearly from D1 to D2. At position X, the diameter is D1 plus the quantity D2 minus D1 multiplied by X over L. The area is pi by 4 times the square of this diameter. Substitution into the general integral gives delta equals 4p over pi e multiplied by the integral of dx over d of x squared. After integration, the compact result is 4pl divided by pi e d1 d2. This expression applies to a circular frustum with both end diameters greater than 0. If one diameter is exactly 0, an ideal point remains at the apex. A finite concentrated end load then makes the one-dimensional deformation integral singular, so this formula must not be used for that tip load idealization. Let a vertical prismatic bar hang from its upper end. Take x upward from the free lower end. At a section located at x, the internal force equals the weight of the material below that section. If gamma is weight density, then n of x equals gamma ax dividing by a gives stress equal to gamma x. The stress is 0 at the free end and increases linearly to gamma L at the support. Substituting into the deformation integral gives delta equals gamma over e times the integral of x dx from 0 to L. Therefore, delta equals gamma L squared divided by 2e. Since the total weight W is gamma AL, the same result can be written as WL divided by 2AE. It is half the extension produced by applying the same force W as a concentrated load at the end of the same uniform bar. For a full cone hanging from its base, measure x from the lower apex. Similar triangles show that the radius is proportional to x, so area is proportional to x squared. The weight below a section is the weight of a smaller similar cone. Its volume is 1/3 of the local area multiplied by x. Therefore, n of x equals gamma a of x times x divided by 3. Area cancels when we form stress, leaving sigma equal to gamma x divided by 3. Integration gives delta equals gamma L squared divided by 6e. If a base is the area at the support and W is the total cone weight, then W equals gamma A base L divided by 3. Substitution gives another useful form, delta equals WL divided by 2A base E. This result is for self-weight. It should not be confused with the concentrated load applied at an ideal zero area apex. We now apply the ideas to a statically indeterminate stepped bar. Both ends A and D are fixed. Segment AB is 1.5 meters long with area 1000 square millimeters. Segment BC is 2 meters long with area 1500 square millimeters. Segment CD is 1.5 meters long with area 2000 square millimeters. Young's modulus is 200 kilonewtons per square millimeter. An 80 kilonewton force acts to the right at B and a 150 kilonewton force acts to the right at C. Because there are two unknown support reactions but only one independent axial equilibrium equation. Equilibrium alone cannot determine both reactions. We need one compatibility equation supplied by the fixed end condition. Let RA and RD denote the magnitudes of the support reactions both acting to the left. Overall force equilibrium gives RA plus RD equals 230 kilonewtons. Next, make a cut inside each segment and use the left portion of the bar in segment AB. The signed internal force is NAB equals RA. In segment BC, it is NBC equals RA minus 80. In segment CD, it is NCD equals RA minus 230. These expressions are deliberately kept signed. We still have one unknown RA. Once it is found, RD follows immediately from overall equilibrium. Do not guess the state of a segment from arrow appearance. The sign of the calculated internal force tells us whether that segment is in tension or compression. Because A and D are fixed, their relative displacement is 0. Therefore, the algebraic sum of the three segment deformations must be 0. Write RAL1 over A1E plus RA minus 80 times L2 over A2E plus RA minus 230 times L3 over A3E equal to 0. Use consistent units, convert the three lengths to millimeters, keep force in kilonewtons, area in square millimeters and E in kilonewtons per square millimeter. Solving this single compatibility equation gives RA equal to 77.91 kilonewtons. Overall equilibrium then gives RD equal to 152.09 kilonewtons. The reactions satisfy both the force balance and the restraint condition. Now substitute RA into the three internal force expressions. Segment AB carries plus 77.91 kilonewtons, so it is in tension. Segment BC carries minus 2.09 kilonewtons, so it is in slight compression. Segment CD carries minus 152.09 kilonewtons, so it is in compression. Starting from UA equals 0, the elongation of AB gives UB equal to plus 0.584 millimeters. Adding the small shortening of BC gives UC equal to plus 0.570 millimeters. Finally, the shortening of CD is minus 0.570 millimeters, bringing the displacement back to UD equals 0. That return to 0 is our strongest numerical check that compatibility has been satisfied. Let us finish with a reliable workflow. First, define a coordinate and declare that tension is positive while compression is negative. Second, cut the bar and determine the internal force N of x, including its plus or minus sign. Third, describe the local area A of x and modulus E of x. Fourth, integrate N over AE or add the segment deformations when the quantities are piecewise constant. For a bar carrying its own weight, the internal force at a section equals the weight hanging below that section. For restrained bars, especially a bar fixed at both ends, add compatibility to equilibrium. Finally, verify the result using dimensions, limiting cases, force balance, and boundary displacements. Every slice deforms according to its local force area and stiffness, and the total change in length is the algebraic accumulation of those small deformations.